In this series of horticulture water treatment, we are going to review ORP, or oxidation reduction potential, as a measurement of effective water sanitation. My name is Karan Kurana with Aquapulse Systems. Water is used in a greenhouse for irrigation in sprinklers, sprays, booms, ebb and flow, flood floors, and various other application methods. Water source may be municipal or well, or it may be from a higher risk surface water source such as a pond, lake, reservoir, or river, or it may be recycled water. Water may contain pathogens such as algae, fungus, Phytophthora, Pythium, and other root rot organisms. We want to disinfect and sanitize the water in order to prevent cross-contamination, to reduce microbial load on the foliar surfaces, and on the roots to prevent disease. However, water treatment with a sanitizer will not remove the pathogen once it's infected the plant. Types of sanitizers are broadly either non-chemical or chemical. Chemical sanitizers may be either an oxidizer such as ozone, peroxide, peracetic acid, hydrogen peroxide, chlorine dioxide, or an oxidizer that needs an acid to adjust the pH and to activate it, such as chlorine, or it may be a non-oxidizer such as copper. Chlorine is the most common sanitizer used because it is inexpensive and readily available anywhere. Regardless of the form of chlorine, whether it is liquid hypochlorous acid, chlorine gas, liquid sodium hypochlorite, or tablet calcium hypochlorite, they all become hypochlorous acid or HOCl in its active form when dissolved in water. Other common sanitizers are chlorine dioxide, peroxyacetic acid, hydrogen peroxide, and ozone. So now we have a challenge. Well, we have multiple sanitizer choices, variety of plants, different microbes, many water sources and watering methods. We also have varying flow rates and contact times. So what is the appropriate chemical level? And how much is sufficient to kill the pathogens? And for how long? So ORP is presented here as a single value measurement of the effectiveness of water sanitation for all oxidizers that takes into account all of the above variables. All oxidizers have the ability to transfer and move electrons. This electron activity gains or loses electrons. Those that lose electrons are oxidized, and those that gain electron are reduced. The electron balance that exists is called ORP, or oxidation reduction potential, also called redox potential, and is measured in millivolts. Chlorine, bromine, chlorine dioxide, peroxides, peroxyacetic acid, ozone are all oxidizers and behave in a similar manner and by the same principles. In this example, chlorine in solution becomes HOCl, or hypochlorous acid, and at a pH of 7.5, it is in equilibrium balance between its active HOCl and its inactive hypochlorite ion, or OCl-. Microbes are surrounded by a cell membrane, which is made up of structural proteins. These proteins maintain their shape due to an electron balance. In the presence of a strong oxidizer, these electrons are transferred from the cell to the oxidizer. The cell membrane loses its integrity and disintegrates and falls apart. So it goes to say that faster the transfer of electrons or higher the oxidation potential, the faster you kill the pathogen. There is a tug-of-war for these electrons between the oxidizer and the cell. In this example of E. coli, at an ORP of 450 millivolts, it will take a long time before it will be killed. At 500 millivolts, it takes an hour of contact time. At 550 millivolts, it takes almost 2 minutes. At 600 millivolts, it is 10 seconds, and at 650 millivolts, it's instant or on-contact kill. Some sanitizers, such as chlorine, bromine, and iodine, are pH dependent. In this example, you can see in the yellow graph for chlorine, its activity is great at pH of 6, but is very low at pH of 9 or 10. Bromine follows a similar pattern. Chlorine dioxide, peroxides, peroxyacetic acid, and ozone are not pH dependent. When you put chlorine in the water, that is the total chlorine, some of it will react and bind with organic matter, dirt, debris, plant material, and is lost for disinfection. This is called combined chlorine. What is left over is free chlorine that exists in two forms: the active hypochlorous acid that does all the oxidation and produces ORP, and the inactive hypochlorite ion. The two change in proportion depending on the pH. At a pH of 6.5, you have 95% hypochlorous and 5% hypochlorite, whereas at a pH of 8, you have only 20% active hypochlorous. If you put 3 parts per million of chlorine in the water and the pH is 8, your ORP may be only 500 millivolts, and that is not enough to disinfect. Now, by adding a little acid, you change the pH to 6.5, you create a lot more hypochlorous acid, and the ORP may go up to 700 millivolts for the same 3 parts per million. You have not changed the amount of chlorine, but simply changed its activity. So you may not know if you have enough disinfection by simply knowing how much chlorine parts per million you have unless you measure the ORP. This slide shows the same data on a graph format. In a study done by Dr. Trevor Suslow at UC Davis, you can see that at a chlorine level of a half a part per million, you have 620 millivolts of ORP, with slow kill of E. coli, Salmonella, and total coliform. At 1 part per million, even though the pH went up, you have over 650 millivolts of ORP and got excellent kill. At 2 parts per million of chlorine, the pH went up further, so the ORP came down to 489 millivolts, and the pathogens were not killed. Similarly, at 10 parts per million, the ORP went down lower to 365 millivolts due to a high pH, and the pathogen survived. So it takes at least 650 millivolts to be effective if you want on-contact kill. This is a study that was done on nursery runoff water, shown over time that as ORP increases, there is a reduction in fungus. This again shows progressive fungus reduction on the samples that were taken on that runoff water. In typical water treatment, you would run a ORP of 650 millivolts with 750 to 800 millivolts for fungus. Peroxides and peracetic acid tend to produce lower ORP values and are typically around 400 to 450 millivolts for about 25 to 30 parts per million of chemical. Different oxidizers have different strengths. The higher the oxidation strength, more aggressive and reactive it is, and lower its stability. Oxidation capacity is the amount of ORP it is able to create. Ozone is the most powerful and least stable, followed by peroxides and then hypochlorous. Chlorine dioxide is lower in oxidation strength, so it is not as corrosive or aggressive, yet a small amount can produce a high ORP due to its high oxidation capacity. A water system may be easily automated for disinfection. A single-pass water line injects chemical on a flow proportional basis with a proportional injection pump. A downstream inline ORP sensor may be used for treatment verification and data recording. In a tank system, an ORP controller with an inline sensor can maintain the ORP level by automatically injecting the oxidizer to maintain the ORP on demand, and adjusts itself to changes in demand from the water source or recycled water. A typical automation system will have continuous monitoring, control, data recording. It may also have simple alarms and communication capabilities for data reporting. ORP is measured by a probe or electrode, which is similar to a pH electrode, except that it has a pure platinum sensor tip. It may be mounted in line or in tank and needs about once a month cleaning and calibration. This graph shows a typical response curve for chlorine dioxide dose to ORP. Record keeping is very important to provide historical diagnostic data in order to understand the disinfection trends. Similarly, pH trends help us understand our water system better. Data records may be opened in an Excel-type spreadsheet with tables, charts, and graphs. It's important also to understand dates and times so we have good diagnostic information. With any inline automated system, it's always good to have a secondary validation method to confirm if your system is working efficiently. These can be simple test strips, digital calorimeter, a portable test meter for ORP, or a more sophisticated ORP and pH meter. Calibration of these meters should be done routinely and is very simple to do in 4 simple steps and takes about a minute. Place the meter tip in a known ORP solution. In this case, it is 468 millivolts, and turn the meter on. Press Cal and the display starts to blink. Press the hold button and the readings start to increase. Stop when you reach 468 millivolts. Final step. Press the CON button for confirmation and the display will stop blinking and will read 468 millivolts. Calibration is now completed. This is a short video of the steps we discussed for ORP calibration in this simple meter. As you press the increase button, the readings start to scroll, go around, and slowly increase until you reach 468 millivolts. You then press confirm, and the calibration is done. So identify your water process, select your chemistry, select the validation test device or test meter, select your continuous inline monitoring system, and maintain records at all times. This concludes our lesson on ORP, or Oxidation Reduction Potential. If you have any questions, please contact the Water Education Alliance, or you may contact me, Karan Khurana, at kkhurana@aquapulsesystems.com.